Today we're going to be taking a look at section 7-6. Now, we're going to only cover part of the lesson for today. And our objective for today is to use the number e to write and graph exponential functions representing real-world situations. Then we're going to solve equations and problems involving e or as natural numbers. So, let's take a look at what that involves. Okay, folks, before we get into there, let's begin with a little bit of review to get our heads into the game here a second. Go ahead and pause it and do these 4 questions. It should take you just about 15-20 seconds to do all 4 of these. Okay, go ahead and pause it. Okay, now that you've worked through it, let's go ahead and talk about this a little bit. First of all, you know that you have base 10 right here. And when the base of the exponent is the same as the base of the log, it logs out, and it leaves you with x. On the second one, do you see what happens? Yep, logs out, leaves you with 3w. Third one, remember this is base 10 right there. So again, you still have the base of the log, same as the base of the exponent, logs out, leaving you with z. And the last one, you see, yep, it logs out, and it's left with x minus 1. Alright, so let's get into this lesson now. Let's review compound interest. Now, remember the compound interest formula. The compound interest formula states this. It says A is equal to, now remember A is the amount, okay, after t years. P is the initial amount that you invested or borrowed. R is your interest rate. N is the number of times it's compounded yearly. And of course, T is time in years. Okay, so with that in mind, let's suppose that $1 is invested at 100%, which means R is going to equal 1, compounded n times for 1 year as represented by this function right here. So we plug all those values in there. Now, let's go ahead. I want you to pull out your graphing calculator, and I want you to graph it. Okay, pause it now, and I want you to graph it. Okay, now that you've graphed it, this is what your graph should have looked something similar to. Now, something that I want you to see. I want you to see right here that you're going to see you have an asymptote. You're going to see that the graph approaches this value, and it's about 2.7 right in there. If you were to get closer and closer and closer to that and continue to trace it, you would see it would be about 2.7, and then it would, actually guys, it approaches this, 2.7182818. That number never repeats. It just gets closer and closer and closer. This value has a special name. That number is called e. Now that e is a lot like pi. Now remember, pi was an irrational number. So is e. E is an irrational number as well. Alright, so that's where e comes from. Now folks, if you were to take your graphing calculator and you were to look for a little button called e to the x, or maybe it will go e to the blank, whichever it is, either e to the x or e to the blank. Now, if you were to enter in e and then type a 1 and then hit your return key, what would happen there is it would look like this. You would get 2.718281828, so on and so forth. Now, this number never repeats. It just continues to go. So notice anywhere in here it does not repeat. It just continues to go and go and go, just like pi. Alright, let's go ahead, and with your calculator, here's what I want you to do. I want you to take your calculator and we're going to enter in a function. So, where it says y equals, and you're going to enter in e to the x. That's what you want to do, just e to the x. And when you enter in e to the x, then go ahead and graph it. Okay, so pause it for a moment and you go ahead and do that. Okay, now that you've done that, let's do a little something else. I want you to realize, if you were to take your calculator and punch in f of x equals 3 to the x, okay, if you were to enter that, you're going to find out that these two graphs are almost identical. The 3 here, 3 to the x, I mean, it's off the function just a little bit. They're virtually almost very similar, almost the same. But you're going to find that the 3 to the x is just a little bit steeper than e to the x. Why? Well, 3 is 3 to the x power. E is 2.718 on and on and on to the x power. Now, when you graphed it, this is what your graph looked like. Looked just like this. Now, let's point out some things in this graph. First of all, you found that it crossed right there at 0, 1. Okay? And also, you know that it is asymptotic to the x-axis. So, at y equals 0 is the asymptote. And it comes and it goes up through, and it is an increasing function. Now, look to where the domain and the range is. Remember before we talked about an exponential function? Remember your domain, look over here, your domain was what? Well, the domain was the set of all real numbers. What about the range? Well, the range, remember, was a set of all real numbers greater than a 0. Now, you may want to put that in interval notation. And when we did it in interval notation, we found that the domain was equal to negative infinity to infinity. And the range, of course, was from 0 to infinity. Okay, all right. So, let's stop right there and go on to the next slide. In the next slide, we're going to define what a natural logarithm is. Okay. Now, what is a natural logarithm? A natural logarithm is a logarithm with a base of e. That's the key right there. It has a base of e. So, this is what it looks like right there, log base e. Now, there is a way of writing natural log. So, log base e is the same as saying ln. Okay, log base e is the same as ln. So I could say log base e of x. That would be the same as saying ln of x. All right? All right, now, your calculator handles two types of logs. Even the very simple scientific calculators do. They handle, first of all, they handle base 10, and they handle base e, or the natural log. All right, so take a look at your calculator and see. Do you see a button on there that just says log? Well, that's log base 10. And then look again. You may see another button that says ln. That is natural log. Okay, now, let's take a look at this function right here. Right here I have the natural log, f of x is equal to the natural log of x. Now, I want you to look at this. This was the exponential function right here. Okay? Right there. There's the exponential function. And notice if I reflect it over the line y equals x, that line right there, that's the reflection line, when I reflect it over that, I get this function right there. That function is the natural log function. Notice where this had a y-intercept of 0, 1, this one will have an x-intercept of 1, 0. Notice your domain and range. They also switch. All right, so let's go ahead and take a second here and let me talk a little bit about some characteristics of f of x equals e to the x. So first of all, I see that it goes through the point 0, 1. Okay, now in your notes, guys, make sure you get these special properties down. Notice that your horizontal asymptote was going to be y equals 0. Notice that your domain for e to the x was negative infinity to positive infinity, and your range, remember, was, let's see, it went 0 to infinity. Okay, now, let's take a look at the log function. Notice, remember I said they were inverses of each other. Therefore, it's going to go through the point 1, 0. The vertical asymptote this time is going to be x equals 0. Now, your domain and range switch again. So it's going to be from 0 to infinity for the domain, and your range is from negative infinity to positive infinity. Okay, make sure you get these properties down. Okay, now let's practice one together here. So, first of all, here's your function, and what I want you to do to graph this function that I have here is, first thing I want you to do is I want you to fill out this chart. In other words, you're going to plug, for example, negative 2 in for x, simplify it, and you're going to get a value. Then you're going to do the same for negative 1, get a value. Okay, so go ahead and pause it. You work down through it, and then I want you to graph it over here. in this coordinate plane. Oh, all right, go ahead and pause the video, please. Okay, now that you've paused it and you've worked through it, this is what you should have come up with. So, here's the values. And then when you transfer those onto the graph, this is what your graph should have looked like. Now, for the first time, you're going to see that this graph has changed. It's not, notice it's an exponential growth equation, but it's not asymptotic here. It appears to have moved up one. Not only does it appear that it moves up one, but you know, the point where it used to be here is now right there. So it seems to have moved to the left, to the right 2, and it has moved up 1. Now I want you to see something. Notice this minus 2, notice this 1. It moved to the right 2, notice it's opposite of what you thought it would do, and it moved over 1. So those transformation rules that we have used for parabolas and other functions also work for the exponential function. And for that matter, they also work for the logarithmic function. Alright, we're going to look more at that another day. So for right now, let's go ahead and we're going to simplify a few of these and then we're going to call it a day. So in looking at the first one here, you have the natural log of e raised to the 0.15t. Notice, this e is the same, this is natural log, so that's log base e. So what's going to happen here? Yep, you said it, it's going to log out. And it's going to leave you with just this value right there. So, for our final answer, it will be 0.15t. Okay, now you go ahead and do the next two in the same fashion. Go ahead and pause it, and then we'll come back and look at it together. Alright guys, you've done those, so what'd you get for the first one? Well, hopefully you recognize that this base e is the same as that base e of the exponent, so this is going to log out here. Oh, hold it here. It doesn't quite log out just like that. Notice that 3 right there. What do you do with that 3? Well, you're right guys, you need to take this 3 right here and pull it back up using the power property for logarithms. So it's going to be e raised to the ln of x plus 1 raised to the third. Okay, now this logs out, and it's going to leave you with x plus 1 raised to the third. Very good. Alright, so now let's take a look at this next one here. This next one here, alright, is there anything out here that I can pull up? No, nothing can happen. Okay, I have how many logs here? Well, looks like we have 2 logs here, don't we? Okay, there's a couple ways that we could do it. I could simplify it like this, because notice the base of the log here is the same as the base of exponent, so this logs out, leaving me with 2x right there. Over here, same thing. Base of the log, same as the base of the exponent, so it's going to log out, leaving me with x. So I get 3x, and there's my answer. Okay? Okay folks, that's going to wrap it up for today. When you come into class next class period, we're going to be working on a worksheet and we're going to review some of 7-5 solving for exponential and logarithmic equations, and we're also going to play with some more graphs. Alright guys, I will see you in class next time. Have a good day.